Hello everyone. Today I am going to explain our project bit depth bench where we study the effect of ADC bit depth on quantization, error, noise and overall signal quality. First, let us understand the basic idea. An ADC or analog to digital converter converts a continuous analog signal into a digital signal. During the conversion, the amplitude of the analog signal is divided into a finite number of discrete levels, and the number of this level depends on the bit depth of the ADC. For an n-bit ADC, the total number of quantization levels is given by 2 to power n. So, if we use a 4-bit ADC, we get only 16 levels. But if we increase it to 8-bit and we get 256 level, and for 12-bit we got 496 level. That means the number of bit increases, the quantization step becomes smaller. Therefore, the digital representation becomes much closer to the original analog signal. Now coming to our next part of the experiment. In this project, we compare different ADC resolution and observe how the signal and the quantization error change with bit depth. Here the upper graph represents the original or reconstructed signal. We can see that the reconstructed waveform follows the original waveform. But if we look to the lower graph, we can observe the quantization error. The error occurs because an ADC cannot represent every possible analog amplitude exactly, and it has to round the input value to the nearest available digital level. Um, with a lower bit depth, the quantization steps are larger, so the error is also more noticeable. When we increase the bit depth, the step size becomes smaller and the quantization error decreases. As a result, the signal to the noise performance improves. So, another important parameter is that we analyze here SNR or signal to noise ratio. Higher SNR generally means better signal quality. We also consider ENOB, which stands for effective number of bits. So a converter may be specified as a certain number of bits, but its effective performance can be represented by a lower ENOB. Now, another important parameter is our experiment is SFDR or spurious free dynamic range. SPDR tells us the difference between the main signal component and the large unwanted spectral component of SPUR. In the frequency domain graph, the main signal appear dominant component, while unwanted component can appear as smaller peaks around the noise floor. This helps us understand not only the noise level but also the distortion and unwanted spectral component produced during the conversion process. Finally, we also studied the effect of the dithering. Dither means adding a very small controllable amount of noise before quantization. At first, this may sound strange. Why would we intentionally add noise? The reason is dither can make the quantization error less correctable, correct correlated with the input signal. Instead of producing noticeable distortion or unwanted patterns, the error becomes more noise like and can produce a cleaner spectral behavior. So the main conclusion from this experiment is that the increasing ADC bit depth reduces the quantization step and generally improves the accuracy and signal to noise performance. However, bit depth is not the only factor that determines ADC performance. Noise, distortion, ENOV, SFDR and sampling condition also play important roles. Therefore, the Bitcoin bit depth the bit depth bench experiment gives us a practical understanding of how ADC resolution affect the quality of digital signal and why proper quantization analysis is important in the real world communication and signal processing system. Thank you.